Hello, hello, hello. Have you ever heard of the Pythagorean theorem before? Pythagorean theorem, that's how it's pronounced. I bet you if you asked your parents, someone a little bit older, someone who's been through 7th, 8th, 9th grade already, they could probably say, yeah, I remember that. Because it is one of the most well-known things in math. It's called a theorem. I'll talk about what that means in just a sec. But what we're going to work on in this lesson and the next is this thing called the Pythagorean theorem. So lesson 23 is all about proving it. So understanding what it is and then showing that, yeah, it actually is true and there's ways that we can prove that it's true. And then in lesson 24 next week, we'll get into using it and solving problems with it. Okay, so our goal is to prove the Pythagorean theorem using pictures and algebra. And also, our success criteria, you'll notice there's a number of things here that a lot of it's review, like finding area of squares and triangles, solving basic equations, using the distributive property. Those all things are going to help us to prove this Pythagorean theorem that's at the bottom. Okay, so they're going to come back up. That's why it's in there. We've got to know those things. So, if you look in your notes page or notes book, by the way, this is going to be, we're going to combine two sections. So we're going to go from page 204 to 207. Start at page 204. What is the Pythagorean theorem? So if you read along here, this top chunk here gives us a good little overview of what it is and what it means. So it says a theorem, because it's called the Pythagorean theorem. A theorem is the statement of mathematical idea that someone has proven to be true. So it's been proven true. One of the best known theorems is called the Pythagorean theorem. That's what we're all about here today in these next two lessons. So, the square of the hypotenuse of a right triangle has an area equal to the combined areas of the squares on the other two sides. I know that's a wordy thing, but the way to show it is if you take a triangle, since what we're working with here is going to always be right triangles, so a triangle with a right angle. If you extend each of the sides to make a square, meaning whatever this side length is for like the longest side, which is called the hypotenuse, say that with me, hypotenuse. If you extend that so that all the sides are the same and find that area, so whatever, we're going to use this as c times itself, because they're all going to be c times c, or c squared, that will equal the area of the two smaller squares if you form squares going out from those sides. Okay, and it'll actually help us find missing side lengths of these types of triangles. Another way of stating it below here is the sum of the squares of the lengths of the legs, two smaller things, is equal to the square of the length of the hypotenuse, which is the longest leg, the longest side. And it's often written as a squared plus b squared equals c squared. And usually the a, b, and c go from smallest to largest for side lengths. So the a and b are the smaller ones, the c is the largest, and that's called the hypotenuse. So we're going to explore a couple different ways to prove that that's true in this lesson. And I want to give you a brief overview here on page 204 and 205. I really like this picture at the bottom of 204. I think this is the best way to use a diagram to prove it, to show it. It says in this diagram, one side length of the right angle. So our right angle is the little 90-degree angle, the box there. So one side length, which is called a leg, is 3 units. So 1, 2, 3. There's one of them. That's going to be our A, smallest to largest. And that's 3 units. And one side length is 4 units. That's always going to be our B. So the two smaller are the A and the B. And then the longest side length, which is C, is 5. So we know that you might be looking at this and say, well, 3 plus 4 does not equal 5. And that's not what we're trying to say here. That's not true for right triangles. But what is true is that, get rid of this, a squared, so 3 squared plus b squared equals 5 squared. That's always true for right triangles, and that's here. 3 squared is 9, 4 squared is 16, 5 squared is 25, and you could check that out. 9 plus 16 does equal 25. And the way we showed that is making squares, because if you square something, it really makes a square. The C makes a square, so C is 5, so it's a 5 by 5 square, and that is 25 inside. The A was a 3 by 3 square, that's 9, and the B, it was or B squared would be a 4 by 4, which gets you 16. And that shows it right there, 9 plus 16 equals 25. So that's one visual model. Another visual model that we're going to look at cuts it into shapes, triangles and squares. Okay, and that's what we're going to go into more in depth on the next page. So we're going to, if you would like to pause it and read this, you can read it. But then we're going to go into more in depth on the next page. All right, so you can turn the page. We're going to skip over the reflect question for right now, and we're going to go to page 206. All right, on these two pages, we're going to prove this Pythagorean theorem. We're going to prove that a squared plus b squared equals c squared for right triangles. And we're going to prove it two different ways. We're going to prove it geometrically, which is with the shapes. And then on the next page, we're going to prove it algebraically with letters and symbols and operations, so like adding, subtracting, multiplying, dividing, that sort of thing. And I'm not going to say that you need to memorize these things at all. I would just like you to attach yourself to at least one of them and try to like understand and say, yeah, that actually does make sense. Okay? Your goal is not to have to do this on your own. It's just to understand that, oh yeah, this is why this is true. Okay? That's kind of our goal for today. So let's complete the geometric proof of the Pythagorean theorem. So we have two figures, figure 1 and figure 2, and it's made up of right triangles and squares. So what I would like to do here is to... So look at number 2. Use what you know about supplementary angles and the sum of the measures of the angles in a triangle to show that each angle in the white quadrilateral is above 90 degrees, or in the quadrilaterals above is 90 degrees. Tell how you know this. That all sides of the white quadrilateral are congruent. So the two acute angles in a triangle have to add up to 90 degrees. So just look right here. If this is a right angle in one of the triangles, then the other two have to add up to 90, because 90 plus 90 would get you the 180 degrees. So those two have to add up to 90, which means if you take two of them, which I have this one here and I have this one here, those two have to add up to 90, which means the other one that makes up this line would be 90 as well, because this whole thing is linear, so it makes up 180 degrees. So to put that into words, I'm going to type this out. I could say the two acute angles in the triangles add to 90 degrees. Okay. Because the total of the angle measures in a triangle is 180 degrees. So the remaining angle in the quadrilateral is also 90 degrees. Now, excuse my spelling. That kind of got messy there. And I will fix that. Okay? So that's with the angles. Now it also says, what are the sides of the quadrilateral? How do we know they're all congruent? The sides are all C, which means they're all congruent, which means that it is a square. So that's in figure 1. Let's go to number 3. Now complete the proof. It says justify the statement that the area of the two white squares in figure 2 together is the same as the area of the white square in figure 1. So what we're saying here is we've got it divided up so that we've got triangles, 4 triangles in each that are the base is A and the height is B, essentially. And so if there's 4 in each, we can essentially get rid of the 4, and whatever's left over should be the same. Should be whatever, the square. In this case, it's C, so the area would be C squared. And in this case, we have B squared and we have A squared to find the area of those, which means that since there's 4 rectangles in both, whatever's left over has to be the same. So A squared plus B squared does equal C squared, because that's what's left over. That's what's white. The white space, if the 2 figures are the same, has to be the same. And that's showing it in a picture. So I'm going to type this out again. In each figure, the white space, make that a little bit smaller so you can fit it. The white space plus the triangles fills the whole area. Since the triangles are the same, the white areas also need to be equal. Now, number 4 says, how does this prove the Pythagorean theorem? Well, exactly what we said. The white space in 1 is A squared plus B squared, and the white space in the other is C squared. And to summarize that, exactly what I wrote above, that the A squared plus the B squared equals C squared. Okay? Now, hopefully you followed along with that. Again, we're just comparing areas of the 2 things, so you find the area of the triangles. Now we're going to write that out a little more algebraically on the next page. So let's look at this diagram and follow along, fill in the blanks. This one's a little bit harder to follow because there's a lot of math that's going on. It says the diagram shows 4 congruent triangles, just like before. Write an expression that uses the area of all 4 triangles and the area of the white square to show the area of the whole large figure. Okay, so we want to try to find the area of the whole thing. So each side length is the A and the B together. So each side length would be A plus B, whatever those are. Okay, we're just using it as A plus B. Okay, so if we want to find that whole area, so let's do it 2 different ways. Let's find the area of the entire thing. And that would be actually number 6. So if the square is A plus B, to find the area of the whole thing, you do A plus B times A plus B, which would be the same as, or I guess we can use B plus A, whatever. That's what it shows below. We'll use B plus A. But that's the same thing as just writing B plus A squared. Okay? Now that's one way to find the area of it. The other way to find the area would be to find the area of all the individual parts. So one triangle would be 1/2 A times B. And there's 4 of those. So if you multiply this by 4, you get, well, what's 1/2 times 4? These are the 2 you multiply together. You get 2A times B. Now for the square, it's just C times C, so C squared. So if I add those 2 together, and this is for number 5, C squared plus 2AB. That'll get us the area of the whole thing a different way. Now we're going to see if how those things actually make the Pythagorean theorem work. So number 7 says use the distributive property to expand on what we did for number 6. So I'm going to go back to blue here. B plus A times B plus A. So if you recall the distributive property, it's where you multiply one thing. So in this case, it'll be B. We're going to multiply B times both of the things in the other one. So to multiply both by B. And then the second thing, we're going to have to multiply A by both of the things in the second parentheses. Okay, so that's what we're going to fill in the blank so far. Now let's simplify. That means we're going to distribute again. So we're going to take the B times both things. So B times B, and then A times B. And in here we're going to take the same thing, B times A, and A times A. Okay, follow along. I know it's getting a lot of math here, but let's actually write this out now. B times B is B squared. A times B is just AB. B times A is just same thing, AB or BA, and then A squared. And so when you combine these two, because these are the same, there's 2AB. So we would have B squared plus 2AB plus A squared, and that's just simplifying number 6. So far, I'm going to put in a box of purple. We have this way to find the area, and then the other way is in number 6, which we end up getting this. They're both different ways to show the area of that whole shape, so they both should be equal to each other. And that's why it says, what reasoning allows you to know that c squared plus 2ab, so that's what we had above, is equal to b squared plus 2ab plus a squared, and that's what we had below. So we had this is equal to this, because they both are ways to find the area. We're going to write that in there. They are both ways to find area of the same shape. So they should be equal. So if we take that equation and we say, now here's where a little bit of solving equations comes in, plus 2ab equals b squared plus 2ab plus a squared. So I'm just rewriting what was above. You notice on both sides there's 2ab. So if I subtract 2ab from one side, cancel it out, I subtract 2ab from the other side, that also cancels out. And what's left over is c squared equals b squared plus a squared. Or if I rewrite it, just rearrange it, you get a squared plus b squared equals c squared. So that's algebraic. That's kind of a long way to do it, but it also shows another way to prove that a squared plus b squared equals c squared when we're dealing with things like right triangles. Now there's a ton of ways to prove the Pythagorean theorem, and that's just two different ways, one with pictures and one with actual algebra. But I want to just redirect you back to what we were trying to do. We're just trying to prove the Pythagorean theorem using pictures and algebra, the two different ways. And ultimately, if one of those ways makes sense, you'll understand that for right triangles, a squared plus b squared equals c squared, and then we'll be able to use that to solve things. Okay? So, sorry this is a little bit longer video. We were just trying to prove it a couple different ways. So, hope that helps, and I'll see you next time.